Hello, everyone. So, good afternoon. I've got a brief presentation on the evaluation of a hybrid air handling system, which we have developed for elderly and immunocompromised occupants. So I'll just go briefly through that. So we will mainly identify some of those background context and then elaborate on experimental and modeling work conducted so far. So, of course, we all know that the allergens provide a lot of health issues widely in the UK context, and it's estimated around 900 million of NHS prescription costs. Then, since the COVID, there has been growing concern about the elderly and immunocompromised population having internal exposure issues, and there has been growing amount of climate control spaces. And then there is a need for increased livability conditions in the indoor space in the Western world in general, requiring more heating and warming. Then that all led us to establish a kind of business need for a combi unit. And that also addresses, in the UK context, the growing emphasis on prevention of health underlying conditions, which could be addressed using a better indoor space and healthier conditions. Towards that, we submitted an inquiry proposal to the Prevention in Health and Social Care Committee, supporting a technology-led intervention. So what led to this kind of development is based on the growing need for alternative to fossil-based radiators, and that has led to more ground floor heating systems or increased amount of circulation in the surface to roof environment, mainly for pollutants like PE, particulate matter, and volatile organic compounds. But at the same time, we know that new furnishing materials, which are being introduced, has got a high response to heating related emissions from their surfaces. And then there is also an increased amount of profiling for pollution moving vertically because of the high rise and then damp issues in insulated buildings. So to address all that, we have generated a vertical unit, which has got a combination of both conventional and some kind of innovative techniques to address these issues. So, of course, we have got both the air treatment, the pathogen removal, as well as the warming features inside. And that kind of leads to a combi system. So towards the evaluation, we have mainly done kind of a dedicated experimental campaign over the last 2 years, and that was supported by some CFD simulations to understand the general trends, mainly simulating some of those impractical situations which could not be tested during real experiments towards the changing of the air change rates. So the lab evaluations mainly treated the unit, the vertical unit, into 6 zones, and each of them had got profiles of temperature humidity sensors as well as particle monitoring. And the experiments were done over 2 years, as I said, from summer 2023, 2024, leading to autumn 2025, across different experimental conditions. So if you see, what we have is a feature which could be automated on the system. So it sets up here, and then we have a thermostat which could be regulated to set condition of temperature, desired condition of temperature, where it activates the warming. And then during the warmer month, we know that there will be some excessive heat generated due to the movement of warmer air. And to improve the livability condition during that situation, there is an add-on to the existing feature, which could be introduced during the during the summer months to mainly extract the warmth through some kind of evaporative cooling system. So this is just an add-on using some kind of evaporative cooling during high temperatures indoor space. And the testing was done mainly for the cooling features. For example, on the left panel, you have the response to cooling, where we knew that the ambient temperature was quite high, typical 20, 28 degrees on the day. But then when the cooling feature was introduced, we could see a decline in the temperature relative to the ambient, and that gave us a livable condition below 25 degrees Celsius, whereas the ambient situation was going over 28 to 30 degrees. So that kind of adjusts for a low energy efficiency. Well, when I say for a greater energy efficiency, just using a simple measure without relying on high compression climate control systems. On the other hand, the slight demerit of this was observed as increasing the humidity in the upper space, which could be a kind of an inherent feature linked to increasing the humidity because of the evaporative cooling. On the other hand, there was some comparison of this vertical unit with standalone electric radiator systems because the radiators are quite common and considered as cheap to have standalone in room space. But then what we found is the radiators, if you see on the left, is the profile at different heights of the temperature. And it was noted that the temperature rapidly rises, and then when it is switched off, when it is cut off, it suddenly kind of dissipates very quickly in the higher region. Whereas for our enhanced unit, which is our vertical unit, we could see it more harmonized within all those sampling regions. So basically, the contrasting feature is that while the heating from the radiator could be quite drastically changing in response to the operation of the system, our vertical unit gives a more harmonized and well-distributed heating. And also, because its heating feature is more kind of geared to lower room space, effectively it can improve the kind of damp and other mold conditions in the lower region where they are typically carpeted and high humidity. So those features are very kind of relevant for typical single occupancy or elderly or immunocompromised individuals who may be suffering from some kind of damp or mold issues in those spaces. So on the other hand, we also tested some of the biological pathogens, and those were tested using spectrofluorescence technique from the bioaerosol sensor. And overall, the general impression was that during its operation, we could reduce the biological potency of the particles through UV treatment quite effectively. And then some dedicated experiments were done using known viruses, and that yielded up to 4 log 10, which is kind of a significant reduction in the control environment. This was followed by some dedicated modeling work where we wanted to test some of these features. And towards that, we introduce, first of all, the design constraints in terms of what flow speed of the actual system would be relevant and how much would be typical performance energy demand to address room size of UCA setting. So we tested different scenarios ranging from different speeds of the fan, different heating systems, and then accordingly we optimize it to reach kind of a standard designed for the first unit. So as we know that there is a vertical profiling in any typical room space, which has got a very kind of moderate to increasing temperatures as we go in height. So, but then at some point, the temperature starts receding again back if for the height concerned. So basically, we wanted to utilize this feature to improve its convection in the system so that the energy demand remains lower. Now, we tested, as we said, different combination of heat flow as well as fan speeds to come up with our central tendency where we wanted to improve this well mixing within the whole region, within the room space. And overall, it was found that different air speeds or air changes could be still using a standard fan speed of up to, let's say, we had and so 28 liters per second was considered too high. So we stuck to our harmonizer speed of B, which was 2.8 liters per second. So then obviously we tested also the design of the outlet because our main unit has got a unique feature where we wanted to improve the ambience or the performance in the lower space. So the vent is located in the lower part, and so we compared the design of our system with a kind of an existing units which typically have got outlets at the top. So we consider that as a switched inlet. So our innovation is mainly trying to use the switched inlet as a feature. And towards that, as you can see, the conventional systems, the existing systems, if we consider the temperature within the room space, the higher the outlet, it kind of releases the warmth much in the upper region, which is beyond the height of the human, so it's beyond the livable space. Whereas in our case, we noted that the releasing of the warm air in the lower region get it well mixed due to the convection, natural convection in the room, and at the same time it doesn't overheat in the human livable space. Likewise, the mean age of air, which is the number of air change required. So the freshness of the air, I mean, how much time it remains fresh is determined using the same design. So first one was our design. The other one is the typical systems which have got outlet at the top. Again, it was noted that during the normal operation without any induced heating, you see the red spots, which are like the stale air, this kind of representing the stale air. So we noted that the amount of freshness in the room is deteriorating if we have got more of the air release from the top. And in our case, as you can see, the amount of time, the mean age of air, sorry, is lower. So it improves the freshness here. On the other hand, with the introduced heating, it increases the convection, and that means that if you can see, our system has got much well mixed. So the span of the air in the room is much easier, much lower. So that means that it is well mixed. So the longer the air remains in an area that is considered as a sign of poor age and poor air conditions, whereas if you have got lower mean age of air, that means it has got good mixing. So that is what we are trying to show. There were some energy calculations, evaluations of mainly the typical operational energy required. And we also did some comparison between a typical um, a standard unit, whereas we operated constantly over a period of time compared to a normal um, heat pump, which is operating over the same period. And we compare that to come up with our criteria where we consider that for a typical 12-hour operation, um, we would be having, because it's automated, we will be only requiring to run the unit for half of that time, and which would be effectively saving the energy. And then we did some calculation using a typical electric unit cost. So we noted that the features A of pollution and pathogen removal, and B of improved freshness of the air, as well as circulation in the lower portion for improved um, uh, improved kind of air environment, as well as lower mold growth conditions, is key to our unit, and hence we consider it would specifically benefit population who are very much sedentary in nature, in one living space or typical room environment, and also kind of vulnerable to pathogen exposure in those regions. So while the warmth is effectively helping both the room environment as well as the individual, the removal of pollutants and pathogens is also effectively producing or providing healthier space for those individuals, hence reducing their vulnerability to grave health conditions or related health conditions. So that's what we have identified to date, and we are trying to explore further customization of the unit through better customer validation and engagements in the community over the next few weeks and months. So yeah, means our results are at the moment is a combination of both summer and winter experiments, where we found that the average livable temperature between 20 and 25 could be maintained in both conditions during the winter through the accelerated warmth by trapping the circulating heat, and also through the additional heat generated during UV operation and supported heating unit, and during the warmer month through evaporative cooling using our water bath. So the pollution is more effectively removed by our system in the region where it's trying to move up after the human activity. So it's kind of conduiting the pollution generated during the human activity zone at the height which could be extracted, and then clean air is coming out from the lower region, which is very relevant to elderly population who are sedentary in that space. And so it, as I say, it's more related to clinical space and community which has got elderly population like care homes, as well as individuals who are more immunosuppressed. So these are the key beneficiaries or potential beneficiaries in our eyes. So we would be mainly targeting some of these to take forward the technology in the next level. So yeah, our team includes myself from the Montfort University as the Royal Academy of Engineering Industry Fellow, who was supported through a 2-year project, and then Richard Little and Peter Rowe were from Genton International, who helped in designing and evaluations of the actual fabrication. And then Guy Whitaker helped us to do some consumer engagements through his expertise in Dynamics grad system. And that's it. So I believe that has kind of given you a snapshot of what we are trying to do in this project, and then further evaluations to let us know. I think at any point we will be happy to contact if you go on my website, and then you can just contact me directly from there, or you could write to me at abhishek.tiwary@tmu.ac.uk. Thank you very much, and hope to hear from you at some point soon. Thank you.